You want to maximize profit, minimize cost? And I think we're at number 7, cost. Yeah. What are the dimensions of a rectangular field of 20,000 square feet that'll minimize the cost of fencing if one side costs 3 times as much per unit length as the other 3? Okay. You are fencing in a rectangle. Your constraint is you must enclose 20,000 square feet. Square feet. You know, I could have mentioned this before. I don't care about units. Yeah, when I'm working the problems, I should label my units, square feet and so forth. But, you know, if you didn't, I wouldn't mark it down. So, that's our constraint. You must enclose that much. And our objective function. What is our object? Our object is to minimize cost. Now, what it says is that 3 sides are cheap, 1 side is expensive. And here's the way a mathematician would think about it. But if you just want to put in some numbers, that's okay too. So, a math person would think, okay, cheap side is $8 per foot, which makes the expensive side $3 per foot. And so if this is the cheap and if this is the cheap and if this is the cheap, then this one is the expensive. And so our question is, what are the dimensions? It's a rectangle. So let's call the width X. Let's call the length Y. Okay. And so, as I say, a math person would say, okay, here is X feet at $8 a foot. So that would be X times A. And here is Y feet at $8 a foot. And here's cheap side at $8 a foot. Which leaves you with the expensive side, which is 3 times as expensive. So all in all, your cost function turns out to be AX plus AX is 2AX, and AY plus 3AY is 4AY. Okay. But I have taught this often enough to know this bothers some of you. You'll ask me later, where did I come up with A? Let's say you just put numbers into it. Make it $10 and $30. Fine. That's great, as long as one side is 3 times more expensive than the other. I've come to learn from experience that you prefer raw numbers. So this is what a math person would do. Many of you prefer raw numbers. And that's perfectly fine. So if you want to say the cheap side is 10 bucks, 10 bucks, 10 bucks, and 30 bucks. If you'd prefer just stick numbers in, or you want to put 1113, fine. Just as long as the expensive side is 3 times more than the other. So, as I say, I think many of you prefer the purple to the blue. Because then you'd say to yourself, okay, look, I got X, I got Y, I got X, I got Y. This cheap side X is 10 bucks a foot. This cheap side Y is 10 bucks a foot. This cheap side X is 10 bucks a foot. But here your expensive is $30 a foot. Do you see what I'm saying? It makes no difference. If you want to call the cheap side A, if you want to call the cheap side 10, it doesn't matter. As long as the expensive is 3 times greater. So all in all, you come down to a cost function of 10, that's 20x, and 10 and 30 is 40y. Okay? And so now let's continue as before. We want to take a derivative and set it equal to 0 because something is optimized at a critical point. But in order to take the derivative, we've got to eliminate y. How can we eliminate y? Well, we're told that you must enclose your constraint. You must enclose 20,000. If it weren't for the constraint, don't build it at all. The cost is 0. Y'all, in these problems, you have to have some kind of constraint. And you're told you must enclose 20,000 square feet. Well, if the rectangle is x by y, there you go, x times y got to be 20,000. So use your constraint. We've done this in several problems. Use your constraint to find y in terms of x, and then stick that expression for y into there. And so now your cost function as a function of x is 20x plus 40 times 20,000 over x. Or you can do the arithmetic. 4 times 2 is 8 with 1, 2, 3, 4, 5 zeros. And so I want to take the derivative, but you know how to take the derivative here, right? Because this x in the denominator is the same as x to the negative 1. So now when I take the derivative of c prime, the derivative of 20x is 20. And so this 800,000 is coefficient, it stays. The old power is the new coefficient, the negative 1 comes down. The new power is 1 less, negative 1 minus 1. Are we okay? Is there anything you want to ask about? So, you take your derivative and you set it equal to 0 in order to get the critical points. Well, isn't that saying 800,000 over x squared equals 20? Move that to the other side. So isn't that saying x squared is equal to 800,000 over 20? Kill is 0. 2 goes to negative 4. So therefore, x is 200. And let's double check. This is supposed to be a minimum. But if you have a minimum, you better have concave up. So let's just double check. C double prime becomes negative, negative. 2 times 8 is 16. Over now x cubed. And sure, put 200 into that, it's positive. The numerator is positive, the denominator is positive. C double prime at 200. I don't actually, sure I could work it out, it's not hard. But all I care about is the numerator's positive, the denominator's positive, the fraction is positive. So concave up. So minimum at x is 200. I guess the only other thing to do, let's get y. Remember coming back up here? Y was 20,000 over x. X is now 200. So I got y is 1,000. Oh, I got too many zeros. It's 20,000. 20,000. Sorry. Too many zeros. Y is 100. So you want to build a 200 by 100. Are we okay with that? Anything you want to ask?
On the exam, are we gonna have to like prove if it's like concave up or concave down?
Yeah, you should check it. So you've raised a very good question. So on the exam, you should check concavity. Yeah.
How did you know if it was concave up again?
Oh, okay. Because remember, where a curve is concave up, the second derivative is positive. Where a curve is concave down, the second derivative is negative. Do you remember in the last chapter, we made up those tables, concavity? So where the second derivative was positive, that's where your concavity was up. And in order to have a minimum critical point, you need your concavity to be up.
Thank you.
Are we okay? Let's take a look at number 9. Yeah. A bus company charges $10 per person for a sightseeing trip if 30 people travel in a group. If for each person above 30, the company reduces the charge per person by 20 cents, how many people will maximize the total revenue for the company? Okay. Yeah, reading this over, there are two ways you could look at it. Do you want X to be the total number of people or the total number of people over 30? You could work it either way. A bus company charges $10 per person for a sightseeing trip if 30 people travel in a group. If for each person above 30, the company reduces the charge per person by 20 cents, how many people will maximize the total revenue for the bus company? So let's let X be the total number of people above 30. So you start with, so P's your price. And what the company is saying is that they're gonna charge you $10 per person, but for each X above 30, they're knocking 20 cents off the charge. Does that make sense? So if I let X be the total number of people above 30, the smallest X can be is 0. That would be just 30, and the price would be $10 a person. And so therefore, you're trying to maximize revenue. Revenue R is, of course, price times quantity. So the price is $10 a person, but they knock 20 cents off for every X above 30. And so the total number of people is 30 plus X. So the smallest X could be is 0. And there you just have 30 people at $10 a person. But then for each X above 30, 31, 32, they knock 20 cents off the price. Okay, so your revenue function in terms of R is, can I FOIL, is that okay? 10 times 30, 300, minus, here I have 10x, FOIL, so 10 times x minus, and here I have 30 times 0.2x minus 0.2x squared. Is FOIL okay with everyone? Multiply these guys here. Multiply these guys here. So let's simplify 300 plus 10x, let's see. 0.2 times 30 is 6. 2 times 3 is 6. And so 10x minus 6x is 4x. So there's our revenue. And the question is, what X maximizes revenue? Let's find the critical point. So R prime of X is, well, the derivative of 300 is constant 0. The derivative of 4x is 4. And here it is 0.2 times 2x, but isn't that double 0.2 to 0.4? So you set that equal to 0, and you come out with x is 10. And so we're supposed to maximize, let's check concavity. Check that this is a max R double prime would be, just negative 0.4, which is negative, which is concave down. So remember, if you have a concave down, you have a max. So they want 10 more people. The company wants 10 more people. X equals 10 more people will maximize revenue. Kind of a cute problem in that, you know, most of the time you're trying to maximize your profit. But here, the cost to the bus company is the same, whether there are 30 people or whether there are 40 people. Because you got to run the bus, you got to pay for the bus driver, got to pay for the tour guide. So your costs are the same. So here's a good case where you really do want to maximize your revenue because your costs are the same either way. Are we okay? Okay, number 16. Find the most economical proportions for a closed cylinder that will hold 16 cubic inches. Okay. You are making a closed cylinder. And how many had your oatmeal this morning, right? Quaker Oats, nice cardboard cylinder. You're constrained. This thing needs to enclose 16 cubic inches. And it says the radius is R and the height of the cylinder is H. Now, you need to know the volume of a cylinder. Yeah, I'd expect you to know the area of a rectangle. I expect you to know the volume of a box. But if I ask you some question like this, I'd give you the formula. I really wouldn't expect you to remember the formula for the volume of a cylinder. Although there is a quick way, it's area of the base times the height. But volume of cylinder. The area of the base is pi r squared, and the height is h. But, you know, I wouldn't expect you to know that. I give you the volume formula. And it says the most economical proportions. In other words, you want to minimize your surface area. Say you're making this thing out of cardboard. You want to use the least amount of surface area. So your objective function. It says most economical. Does it make sense that is saying the least surface area? Because that's saying the least amount of cardboard. Make sense? So I need the surface area of this thing. Is it clear how to find it? Again, you know, I'd give you this. But imagine if you took your cardboard box and cut it and splayed it out. You've got the top. The top is the area of a circle, which is pi r squared. Likewise, that's the same as the bottom. Now, how about the side? So imagine making a cut. Make a cut there and lay open the whole cylinder. Well, that's still height h, right? And that there is the circumference all the way around. That's the circumference of the circle. Which is 2 pi r. Again, I would give you that. So the side is a rectangle, length times height. The side is 2 pi r h. So your objective function, I'll call it surface area, SA, surface area. So it's got a top and a bottom, 2 pi r squared. So a top and a bottom. And then it's got all the way around the side, which is 2 pi r h. And our constraint, 16, is h pi r squared. All right, so as before, we want to take a derivative here, but it's got an r and an h. Let's eliminate the h. Go to the constraint, and you find h is 16 over pi r squared. Put that into your constraint. So your surface area is 2 pi r squared plus 2 pi r h, but h is 16 over pi r squared. Now you've got some nice cancellation, pi over pi, r over r. So that gives you 2 pi r squared plus 2 times 16 is 32 over r. And that's not a hard derivative, right? Because you know that r in the denominator is r to negative 1. So therefore, the derivative with respect to r of your surface area is 4 pi r. Was that okay? 2 pi is a coefficient, it stays. R squared goes to 2r. Here we have a minus 32. The old power is new coefficient. New power is 1 less. Set that equal to 0. In other words, you've got 4 pi r is equal to 32 over r squared. Move that to the other side. Let's see. I can divide by 4. That'll divide through by 4. Pi r equals 4 goes into 32 8 times. So divide through by 4. And then I've got r cubed equals 8 over pi. So r equals the cube root of 8 over pi, well, the cube root of 8 is 2. And so your radius is that, and the height would be 16 over pi r squared. So that's 4 over pi to the 2/3, or 4 goes to 16 4 times. That's pi to the 1/3. Okay, so that's 4 times the cube root of pi. So as it turns out, the radius is twice the height. But as I say, if I gave you something like this, I'd give you the formulas. I wouldn't expect you to know, remember the geometry. Are we okay? So that brings us up to a new topic. Yeah. Before I leave this step to this step to this step reminded me of a mistake a bunch of you made on the last midterm that I want to talk about. So let me talk about that mistake. On the last midterm, many of you made this sort of mistake. Let's say we want to find the derivative of the square root of x. Okay. In order to use the power rule, I first turn that root into a power, x to the 1/2. So from here to here is algebra. Now I can do the calculus. Calculus says the derivative, the old power is the new coefficient, the new power is 1 less. Meaning if my power is 1/2, I subtract 1, and I get negative 1/2. The mistake, here's the mistake. What you did was just the algebra. You thought by turning the root into a power you were done. No, that's only the algebra. Rewriting the root as a power 1/2, that's algebra, not calculus. Here's another one. If you have 1 over x, okay, Here's the correct way to do the problem. You need to know your power. 1 over x is x to the negative 1. Now you can use your power rule. The old power is the new coefficient. The new power is 1 less, or that's negative 1 over x squared. The mistake, people thought that doing the algebra was enough. No. You do the algebra in order to apply the power rule. Don't just do the algebra and stop. That's not yet the derivative. Okay? So be careful with that. What we are using to take the derivative in this case is the power rule. And you remember, if you have x to the n, you remember how to take the derivative. The old power is the new coefficient. The new power is 1 less. Okay. Now, I also want to say this. Because now the new material is we're starting to use this backwards. And that's often confusing to people. What have we learned? We've learned the power rule. What else have we learned? We've learned the product rule. That if you want the derivative of product, say p times q, what you do is the staggered product. You take the derivative of p times q untouched, and then add to it the reverse, p untouched with the derivative of q. That's the product rule. Remember, we've learned quotient rule. If we have p over q, remember what you did. Denominator times derivative of numerator minus numerator times derivative of denominator over the denominator squared. Again, several people made the derivative of the quotient of the derivatives. No, it's more complicated than that. And then remember we had chain rule. That if you have an outer function and an inner function, you first take the derivative of the outer function and then multiply that by the derivative of the inner. So I wanted to summarize these 4 rules because with these 4 rules, I basically can throw at you any function whatsoever, and you can find its derivative. It might be a chain rule inside of a quotient rule inside of a product rule, but you can do it. Where we're going now in chapter 6 is the reverse. And the reverse is a whole lot harder. What do I mean by reverse? Here, you're taking the derivative of a function. What we're going to do in chapter 6 is I give you the answer, and you come up with the function from whence it came. Let me do an example. So 6.1. I'm sort of sorry for the term, but we're stuck with it. These are called antiderivatives. Well, all of this stuff was done back in the 17th century. And the words were slightly different back then. Today we think of anti meaning against. Anti-war, anti-hunger, right? You're against hunger. But back in the 17th century, anti meant before. So if we were coming up with the words today, instead of antiderivative, we probably would say prederivative. What comes before the derivative? And so here's what I mean. Let's play a game. I'm telling you that the answer to the derivative is 2x. What I need you to do, I need you to tell me the original function whose derivative is 2x. Have you done enough of these to know? Your answer is going to be 2x. What do you need here? X squared, yeah. Make sense? Are you familiar enough with your rules that if I tell you 2x, you could tell me that it came from the derivative of x squared is 2x. You also could have said x squared plus 5, 113, right? You could have said x squared plus any constant, because of course the derivative of a constant is 0. Let's push it. Let's keep going. What if I asked you, have you ever watched Jeopardy? They give you the answer, you got to come up with a question, right? I tell you that the answer is 3x squared. Can you tell me the function that it's the derivative of? X cubed. And if you want, you could say plus c. X cubed. So that's why we're calling these the prederivatives. The term is antiderivative. I give you the derivative, you come up with the original function. Okay, now let me modify this first one a little bit. Let me see if I can fool you. Instead of 2x, I want the answer to just be 1x. What is the function whose derivative is just x? If x squared is 2x, I want just x. How do I modify this? Does this make sense? If I wanted only x for my answer, how about if I take the derivative of half x squared? Does it work? 1/2 is a coefficient, it stays. The derivative of x squared is 2x, and 2 over 2 is 1. Does that make sense? Here, let me play the same game down here. Instead of 3x squared, I just want to end up with 1x squared. How do I modify this? A third? If I had a third x cubed, wouldn't that do it? Because if I take the derivative here, that's 1/3, x cubed becomes 3x squared, and the 3's cancel. Okay? I'm leading up to a formula. So there's a formula coming. You don't have to do a bunch of guessing. But I'm trying to warm you up to the formula. So let me take it another step. If I ask you for the derivative of x to the fourth, you'd all be happy. The derivative of x to the fourth, old power, new coefficient, new power, one less. Happy with that. But now what if I ask you for, I want to come up with a function whose derivative is just x cubed. I don't want a 4x cubed. I want just x cubed. How would I modify this? 1/4 x to the fourth? Let's see, wouldn't that do it? So, do you see what I'm leading up to? If my integral is to be x to the n, what did I need here? Oh, I know. Let me put in a step. Before I ask you that, let me ask you this. I've got x to the n plus 1. You're all comfortable with this. I want the derivative of n to the x plus 1. And you would say, okay, sure. Old power is new coefficient. New power is 1 less. And of course, the derivative of a constant is simply 0. And so, now I'll ask this. I want you to come up with the pre-derivative of x to the n. In other words, what do I take the derivative of in order to come up with x to the n? Well, it doesn't have to be x to the n plus 1, 1 over n plus 1. Did that make sense? That's what I was doing up here. If I wanted it, x cubed is my derivative. The pre-derivative has to be what? Well, it's got to be x to the fourth. But if I don't want the 4 there as a coefficient, I need a coefficient of 1/4 here. Does this make sense? You see, this is nothing more than your power rule backwards. This is your old power rule backwards. And there is a symbol, right? Math has a symbol for everything. The symbol for pre-derivative looks like this long stretched out S, pronounced integral. The integral of x to the n is 1 over n plus 1 x to the n plus 1. This long stretched out S means give me the function whose derivative is x to the n. Now, there's also the symbol, they stick the symbol dx over there. And just think of these two symbols like left and right hand parentheses. They do have a meaning, but don't worry about it. So think of these really as just one symbol. And it's the symbol for antiderivative. What is the function whose derivative gives you that? And so this is called integration. And next time I'll talk about integration is hard, which is kind of surprising because you guys can basically take the derivative of anything I throw at you. Between those four rules, power rule, product rule, quotient rule, chain rule, you can differentiate anything inside. But it's easy to come up with examples that not just you can't integrate, not just I can't integrate, but they can prove cannot be integrated, even though they look simple. So I'll pick up talking about integration on Monday. See you later.